Okay, so continuing with the wavy wall problem, right? So we were supposed to find out the velocity, surface velocity potential. Okay, so what given the equation for the contour of the wavy wall. So what we found out were basically these two relationships. I think I wrote it like that. Right. So this is what we got. I think we call this as equation G. Now this is something we got using the contour equation of the physical contour equation of the wall itself, which was given to us, right? We got that, and then we use the while solving for the equation, governing equation, we used a method of separation, and then using that, so numerically we got again this relationship again at the wall. We also got this to be right, and we said, say G, this was I, so this equation was, I think, I. So this is where we kind of stopped in the last lecture. So so now what is left to do is basically equate, you know, this expression and this expression. So essentially this is also, right, and this is the equation we got because we said that our solution is basically, right, because we said this equation resulted from the fact because we said phi p was, right, and then we got expressions for fx and gy, and we were using boundary conditions, right, we were using boundary conditions. So this is essentially our fx out here, and using boundary conditions, which is at the wall. Now since here we said that this is going to be small perturbation, so which means that h is very small, okay, and which means that y at the wall is nearly y is equal to 0, right. So this is where, so we got these two equations. Now if we have to equate these two, so you can, therefore these two can be equal only, of course. So we've got basically, you can see we got a sine term here, we got a sine term here and a cos term here. So for if G, if we equate I say, okay, so if we equate these two, so this is going to be possible only if, right, only if we can do this only if this is possible. So if this is true, and of course also so essentially, and also here, if because there is no cos term on this side, so this b2 of course needs to go to 0, and if you see this in here, this omega term also needs to be 2 pi by L. So there we go. So we found something for these are the two relationships, right. So therefore if we had to write this, okay, so let us say write this now with b2 equal to 0 and omega being equal to 2 pi by L. So if I do that, so therefore what we get is this, right. Okay, and okay, is equal to this, right? So therefore, so what we get is A1 B1, right? So now A1 B1, okay, sorry, I missed out the negative sign here. So what we have here is that A1 B1 is equal to 2 pi by L, so 2 pi by L, so that goes off. So omega is equal to 2 pi by L, so that cancels out. So what we get here is H phi infinity, okay. Right, so this is what we get from here. So let's sort of look at this one more time. So here, now this omega is equal to 2 pi by L, which we just found out, right? So therefore they cancel out, and again this term sine omega x, and this is also the same, so they cancel out, okay. So therefore we are basically left with A1 into B1, right, is equal to H here, V infinity here, and we take this down here. So therefore A1 B1 is equal to this. Now what we had from earlier, like we said, that right, it was this, right, and our equations, so therefore now fx is now become, so fx essentially, so fx becomes with b2 equal to 0. Okay, let me write this again. So we had written fx, to be right. So here now this fx now becomes omega is 2 pi by L, right. So fx becomes this, right, because we said we found out that b2 is 0, right. So again let's go here. So gy was given by this, okay, and we also said that because at y tends to infinity, for this to remain finite, so this was the condition that we used, so that gy therefore becomes two pi by L again for that, to 1 minus y. Okay, so again this is my expression for gy, right. So let us therefore now write which we get as okay into this is my fx, and to gy, which is a1 e to the power into y, right? So, or we can basically, now what we know here is that this a1 b1, we got an expression for that. So, a1 b1 is h into v infinity by this. So, we could actually use that there, right? So, or we could write as a1 b1 is h right, that. Then we have the exponential term, right. So, then we have, say, let me write this like e to the power minus 2 pi by 1. This, right, right. So, therefore, this is my perturbation potential, right. So, then this becomes my perturbation potential. So, I think I have called this as equation 9. So, let us keep this as equation 9. So, now that we have got this, our original problem was that we needed to find a surface velocity potential, right, and we said that we were going to divide that or fraction that into the free stream and a perturbation potential. Right. So, basically we said that this was equal to, right. So, this was the perturbation potential and this was the free stream. So, now we have got an expression for this in here. So, to this if we add this, then therefore, we get the total velocity, total surface velocity potential. This is what we get, right. Okay. So, now the next task was that now having found this, we have got the first job out of the way. The next job was to find out a surface pressure coefficient. We also needed to figure out what the surface pressure coefficient would look like. Okay. So, let us see what that means. Now, what I am going to start with what you mean by the surface pressure coefficient. Okay. So, we will call that basically as it's pressure coefficient. So, you sort of write that as Cp, right, and you essentially say okay. So, this is the dynamic pressure and this is the static pressure difference. So, this is our coefficient of surface pressure coefficient. Okay. So, now we need to get an expression for this over the wavy wall. Okay. So, let us see how we will do that, or if we can do that from here or not. Okay. So, let us look at this and use this. So, this is, we need an expression for this essentially. This is my surface pressure coefficient. Okay. Now, let us use this. Right. So, if I do that, then what we get over here, if you see, right. So, what I am going to do is half this rho infinity, right, this rho infinity I am going to write in terms of right, and right. So, therefore, you can pretty well see from here. So, therefore, this can be written as what? This can be written as Okay, so therefore this can be essentially written as 2 by gamma, okay, into p minus p infinity by p infinity. Right, the same thing I can write this way. So you can see here that this makes some sense to us, right? So this I can write as the Mach number. So therefore I can write Cp, okay, to be 1 by into okay. So therefore I've now basically transformed this equation into this, introducing the Mach number, right? So we have the Cp over here, which is now written in this form. Okay. Now, so essentially what we're seeing here, that this sort of solving a problem like this involves a lot of mathematics, right? It's mathematically pretty exhaustive. Okay, so okay, so now having done this, okay, now total enthalpy here is constant. Okay, total enthalpy here is constant. So say I take any point in the flow field. So basically what I will have is right. So this is it. Now the reason I write this is because total enthalpy is constant. Okay. Now for a calorically perfect gas, we also know that this is equal to, we know this, right? So if we know this, then let us write this out. So for this equation becomes right. So if I do this here, okay, and then okay, so let us sort of, I'll kind of not skip steps here maybe. So then what we do over here, let us divide by Cp, right? So what we get here is dividing by Cp throughout. So if I divide by Cp throughout, what I get is this. Right, this is what I get, and again, okay, so again what we get over here is, so T minus T infinity is equal to two into Cp, right? Now this Cp again can be written in terms of the gas constant and gamma. So therefore this again I can write as right, this is my Cp here, if I write it in this term, right. So if I do that, so therefore again I divide by T infinity, right. Then this equals to right. I divide by T infinity throughout. So if I divide by T infinity throughout, this is what I get, right? So you can see this gamma r T infinity is equal to what? A infinity squared, right? Speed of sound. So what we get, so therefore we can write this as, say we can write this as right, this gamma r T1 is equal to A infinity squared, right? A infinity squared. So now if you look at this term here, so therefore what we essentially are looking at, okay, so let us clear out this, okay. So what we are looking at is this. Okay, into so this is what we are looking at this point here. Now let us see what this v looks like, right? This is the local velocity, right, and this is the free stream. Now as we have said earlier, okay, as we said earlier, now u is v is what? V is the free stream plus the perturbation potential, right, plus the perturbation velocities basically. Okay, so this is my local velocity, isn't it? So therefore when we say v square, right, when we say v square, it is equal to what? It's basically equal to this, right? So if I do this, what I get from here, so what I get from here is essentially, so this, then this term becomes right. So therefore I can write this whole v square term as, so therefore v square becomes this, right, this, right. So total v square term is this. Now what we have over here is, in here t in this particular expression is v infinity square minus v square. So v infinity square, so v infinity square minus v square then becomes right. This is what we get. So therefore our this term here, t by t infinity, right. So t by t infinity then becomes, I take the 1 to the right hand side, okay, 1, and so this becomes, the whole thing is a negative, right. This right, and by a infinity square, this whole thing by a infinity square, right. So this is what we get using the as t by t infinity. Hopefully now you're seeing where we are going. Okay, so let's kind of just stop for a little while and see what we were doing. There's so much math involved, sometimes you kind of get muddled at where we are going, right. So we have to find out the surface pressure coefficient. So we started from this, right, and then if for this density term here, from this density term here we introduce the speed of sound in the free stream. We did that, and consequently we were able to introduce this Mach number. So what we were able to get from this what we were able to do here is write this term in this fashion, introducing the Mach number. Now having done that, we went back and said that the total enthalpy is constant. So we started with this equation, right, and what we have done here is essentially worked with this enthalpy constant, this relationship, and got an expression for T by T infinity, right. We just did the math out here and got T by T infinity to be in this form. So clearly what we will do now what we need out there, however, Cp is P by P infinity. We have got T by T infinity. So we will basically use the isentropic relationship, right. Okay. So having done that, so what we will now use is the isentropic relationship, right. So we have from isentropic, so right, so that means that this is what we get from isentropy. So we actually have a relationship for P by P infinity, which is related to T by T infinity. Now, T by T infinity, you can see we have written here in terms of just the velocities, right. We have written here just in terms of velocities. This helps us in this present case. Why? Because for our present case, we have basically found out the velocity, surface velocity potential. Now, from if that surface velocity potential is known to us, then we can get all the velocities. So in here you can see we have the perturbation velocities and the free stream, right. So this term is basically known to us. So therefore, if I let us write P by P infinity. Now therefore, P by P infinity, so we can write as say 1 minus, okay, right, this okay, raised to this power. Now let us say that, let us call say this entire term, let us say we will call this term as tau, okay. So then so let us call that as tau, and this is what we get, right. Now if we have this, now what we will do out here is expand this binomially. Okay. If I expand this binomially, so we will expand this binomially. Okay. If I do that, what do I get? So then what I get is and so on and so forth, okay, and so on and so forth. So this is how we will get, we are neglecting the higher order terms, okay. Now if I do this, okay, so therefore basically we just introduce this term gamma by gamma minus 1 into this tau, okay. So what that will do, so if we go over there, so what that will essentially do here, okay. So now, okay, so let us go ahead and do the remaining math of this. Okay, so what that does is essentially that P by P infinity is therefore then equal to Okay, so I will just straight away write this. We get a multiply this term by gamma minus 1. So what we get is this right, and then this is essentially, so we have other terms over here. Okay, now we will do a very simple thing. Okay, we'll what we will do here is we will take multiply this by v infinity. Okay, so if I do that, so essentially what I will do is multiply this whole thing by, okay, sorry, this was infinity square. So we will multiply this by v infinity square and v infinity square, right? Now if I do that, then what do I get? So therefore what I get here is right. So this is where I introduce my Mach number. Okay, so and here what I get is this is what we get, right? This is what we get. Now at this point of time, let us introduce the small perturbation theory, right? So small perturbation theory, which means right. So therefore the squares, etc. So if I use the small perturbation theory, so I can basically say that we can ignore this term. So what we are left out essentially is this. So if I am left with this, then what happens to my Cp? Let us see what the relationship that we get for Cp. Okay, so Cp okay, now Cp was essentially this was my Cp expression, and what I have got now is that P by P infinity is 1 minus gamma by 2 into m infinity square, right, into this is what we get, right? This is what we get. So therefore, so P by P infinity minus 1. So therefore, P by P infinity minus 1, this P by P infinity minus 1 is basically this term, okay, is basically this term. So what we get here, so P by P infinity actually is just this term, okay. So therefore, Cp is nothing but this, right, and this is from the yeah, okay, so we have a negative yeah, so we have a negative sign also, okay. So minus 1, so P by P infinity minus 1 is actually negative here. So let's say we include that as well. So essentially this, right. So P by P infinity minus 1. Okay. So if I do that, so this is it. So this is my Cp, assuming small perturbation theory. Okay, so now that we've got this, now we know the expression for, we can find out u dash, because now we know we have an expression for the perturbation potential. So therefore, u dash is basically del phi p del x, right. So therefore, this is the small, from using the small perturbation theory, therefore, the Cp depends only on the u component of the perturbation potential. Okay, but it depends on the, or just the u component of the perturbation velocity. Okay, now let us see if we can draw some more inferences from this. Let us write out this Cp and see what we get. Okay, now since we have phi p, since an expression for the velocity potential, let us see and let us plot. Okay, let us plot that over the wavy wall and see what we get. Okay, so what did we get for phi p? Okay, let us see what did we get for phi p. Okay, so this was our, so phi p was this, right. So exponential that okay. So this was our phi p. So what we need here, okay, so u dash, okay, so u dash is nothing but, right, this is what it is. So what shall we get over here? So this, from using this expression for phi p, what we get is, right, okay, right. So this is our u dash, okay, using this perturbation velocity potential. So then our Cp, okay, coefficient is okay 2 into this, right. So Cp is 2 into u dash by this. So which means that Cp, therefore Cp, okay, Cp is equal to minus 4 pi by L, okay, h by 1 minus, okay, we divide by v infinity, so that so cancels out, okay, and e to the power okay into so now I have an expression for Cp as well. So we have an expression for the velocity potential. So this is the perturbation velocity potential, and add to that v infinity x and you get surface velocity potential, and we also have a expression for the coefficient of pressure, right. Now let us see how this looks like. So this is essentially giving us a feel for the velocities, right, velocities, and this is giving us a feel for the pressures. So let us see physically what this actually means. So if I look at this, okay, Now, so let us write out one more term in here. Okay, so this is my perturbation potential. Okay, this is my perturbation potential. This is the perturbation potential. This is the coefficient of pressure potential, coefficient of pressure expression, and this is what was given to us, right? This was the so this is the wall, isn't it? So this is essentially the actual equation of the contour of the wall itself. Okay. Now, so what you can see is that in here the perturbation potential, okay, perturbation potential is dependent on this sine 2 pi x by L, right, whereas you have the coefficient of pressure which is a cos 2 pi x by L, right. Let us plot this out and see what we get. Okay. For one case we will actually plot the wall, and the other case we will plot the Cp over it. So, you can see that unlike Phi and Cp, the wall and Cp actually vary according to the have the same cosine variation. They have the same cosine variation. However, they have a 180 degree lag, right. So, let us see what that means. So, say we have this wall out here, okay. So, say we have this wall out here, okay. So, we have this wall out here, okay. So, this is the wall, okay. Now, what we have here okay. So, now we have now look at the Cp, however. Now, the Cp, however, is 180 degree phase lag, okay. So, which means if I had to draw draw the Cp on this curve on this plot with respect to this, what I would get is essentially this, right. So, this would be my Cp, and this is how it would look with respect to the wall itself. Okay. Now, what does this mean? Now, what this means out here is that a pressure is acting on the wall. Okay. So, I am going to exaggerate this and draw it like this. So, this is exactly how the pressure looks like. Okay. It will act normal to the surface, which is what I am doing, right. Okay. So, this is how the pressure is acting on the surface, right. This is how the pressure is acting on the surface. So, essentially this is and this is the plot. Okay. Now, let us look at one thing here. Now, let us look at one thing here. Now, we will consider say two these pressure vectors like this. Okay, if I consider this, and let me resolve this. So, say I am considering exactly two pressure vectors here. When I say pressure vectors, I am just meaning these arrows over here, which denoting the direction of the pressure, right. So, what I am drawing here, trying to show here is I am taking exactly two immediately opposite, these pressure vectors, and what I am just resolving this in the x and y direction. Okay. If you look at that, so similarly, say we have, say, take this and this, right. So, then we have right. So, this is what we get. So, if you have this, what do you see, what do you understand from this? If you do that for every other, for all the pressure vectors, for the entire pressure diagram out here on this wall, what will we see? Do you see that? Do you see that the horizontal components cancel each other out, right. So, we essentially have, in this case, as you see, we have this pressure distribution, right. We have this kind of a pressure distribution, which is a 180 degree phase lag compared with respect to the given wall. Okay. And so, then what we see from here is that it is a symmetric distribution, right. It is a symmetric distribution, as a result of which the horizontal components cancel out, right. So, if this is if the horizontal components of the pressure cancel out, what does that mean physically? What this means physically is that there is there is no drag. Okay, that is what it means, and this again, you see, this is physically plausible. So, therefore, that creates what we know as a D'Alembert paradox. Okay. So, what we can, in the end, what we should be saying here is that, let us say, we use what we have done here is we have used a linearized theory. Okay. What we have done here is we have done essentially. So, now let us see what this means to us. Okay. So, what we have studied here is 2D. Okay. We have said subsonic, we have said subsonic, then adiabatic, of course. We have used a velocity potential, right. So, therefore, this was an but this was compressible. Compressible flow. Okay. So, in this case, so this sort of a problem, okay, when we took the wavy wall, okay, we took the wavy wall, we took a 2D problem, we said it was subsonic, it was adiabatic. So, inviscid, we took an inviscid, we did an inviscid solution for this, and we were able to solve equations, etc., etc. What we find, however, is that what we get here is that all the horizontal components cancel out of the pressure. So, that means there is no drag, there is no drag in the x direction, there is no pressure component. So, there is no drag. So, this is what is typically known as the okay. So, this okay. So, D'Alembert's paradox. Okay. Now, also now what we will do here is also look at this pressure here, and you can see that the coefficient of pressure varies according to x and y. Okay. We will just study this a little more, and then we will do the entire problem again for a supersonic case. Okay. So, we will continue this. Okay. Thank you.